Today we start Module 4, Divide and Conquer Approach. Part A, Introduction to Divide and Conquer and Insertion Sort. 8.1, start with Insertion Sort. So this module we will learn a very basic and very important problem-solving approach, divide and conquer. So we used this before. So at this point, we solved several problems, and some of the problems we already used divide and conquer. But in this module, I want to systematically explain, get you understand this very important method. All right, so let's start. First, before we look at our first problem in this part, I want to talk about some general view of this divide and conquer. First, decrease and conquer. So look at this name. This is from our textbook. So in our textbook, it uses this special name, decrease and conquer. So you can see the name is different. It relates to divide and conquer, but use this decrease. So let's look at the, what's the meaning of it? It is a special case of divide and conquer. Divide and conquer is the most popular name about this method. Decrease is not very popular. So how many people know decrease and conquer? So not many people know it. All right. So let's discuss the situation using divide and conquer or decrease and conquer, similar situation. The situation is exploiting the relationship between a solution to a given instance of a problem and a solution to its smaller instance. All right. So here usually we understand in this way, solution to a given instance. So we call it the solution of the current problem. Current problem, so given instance, that's our current problem. All right. Then solution to a smaller instance. So we call it a subproblem. Smaller than the current one. Sometimes we call subproblem. Here we want to connect these two problems, two different instances, two problems, different sizes. There is a gap. We want to bridge that gap. That gap. So we need to do some work to bridge the gap. After we bridge the gap, we get a recurrence relation. So usually we get a recurrence relation. Then we solve that recurrence relation, so then we solve the problem. So that's the typical procedure. Now, how to divide? So there are several different ways to divide the problem. Divide the original problem into its subproblem. You need to divide many different ways. The good thing is at this point, we have used this method several times before. So we can refer to our older problems, solutions to understand this method. First, it's called decrease by constant. Decrease what? Decrease the problem size. Decrease the problem size by a constant. Many times that constant is 1. Most of the time the constant is 1. but not necessarily one. Sometimes could be, more than one. Yeah. So decrease by a constant. Second, decrease by a constant factor. Yeah. Constant factor. When you see this factor, it's a division. Divided by a constant. Divided by a constant. That is a subtraction. So this constant, the problem size, subtract a constant. Here, the problem size divide a constant by a constant. Yeah. So that's the difference. Okay. Yeah. Another case, variable size decrease. We learned that. Remember our GCD problem, right? Greatest common divisor. GCD problem. So the variable size decrease. Yeah. So typically, these cases. Yeah. But here, I like to make some comments on this method, decrease and conquer. Yeah. Based on my opinion, same thing. Same thing. So that's exactly, so things do here exactly divide and conquer. So that's covered, all these things covered by divide and conquer. Although you call decrease problem size, so you see that decrease name, but from the main idea, divide and conquer. So what's the difference between divide and a decrease, right? Yeah. Essentially the same. Essentially the same. So in my opinion, I like to keep the original name, divide and conquer. Yeah. The reason is simple. Yeah. So I highly recommend we use this divide and conquer, not decrease and conquer. The reason is simple. When you talk about divide and conquer, everybody knows it. Everybody knows the meaning of divide and conquer. But when you talk about decrease and conquer, how many people know it? Not many people know it. No. What's the exact meaning of decrease and conquer? So you need to spend a lot of time to explain it. Okay? So it's not necessary. So that will increase the communication cost. When you do the communication using this, strange terminology, so people need your more explanation. So that increases the communication cost. Yeah. Yeah. Anyway, yeah. So that's my comments. Yeah. So when you read a textbook, you can, easily switch to divide and conquer. Yeah. All right. So now we move to the next topic. Recursive or non-recursive. When we solve a problem, we have two options we can use. One is the recursive way, another is non-recursive way. Yeah. So here we are talking about divide and conquer. Okay. When we use the divide and conquer to solve a problem, after we derive that recurrence relation, we have these two ways to solve that recurrence relation. First, just a recursive way. Right? Second, we do not use recursive way. We use non-recursive way or iterative way. Remember, we talked about that before. Fibonacci numbers, iterative way, non-recursive way. Yeah. Here, so let's look at the difference of these two methods. All right. So now, suppose relationship. So here we're talking about recurrence relation. Okay. So the recurrence relation between the original problem and the subproblem derived. Now, implementation. We look at the implementation step. Yeah. So if you just naturally use the recursive implementation, it's okay. That's one of the options. So it's okay. Yeah. But here there is something you need to know before you do that implementation. something behind the scene you need to know before you choose your implementation. So here I want to talk about that part. Changing from recursively to iteratively. Recursive way, iterative way. Changing from. So why we do this change, right? There is some good reason for it. There is some good. So here I may say it this way sometimes. Okay, sometimes you may need to do this. Not always. Okay, sometimes you may need to do this. Not always. Not always. Yeah. But why sometimes we may need to do this change? Reason. First, use less storage space. We can save some storage space using the iterative way. Why? Remember I explained the recursion before. The first time I talk about recursion, I draw this diagram. Internally, the programming language uses stack to implement recursion. You may, when your problem size grows, the stack could be very deep. A deep stack consumes a lot of memory space. A lot of memory space. So that's not good. That could make your program running very slow. Could be, very slow. Yeah. But if we switch to iterative way, there is no deep stack. Yeah. So because we can use temporary variables to store the intermediate results. After that, we just reuse those temporary variables. We don't need a very deep stack. So that's the reason we can save a lot of memory space. That's the most important reason. Yeah. All right. The method. When we do the iterative way, typically we use the bottom-up approach. Yep. That's straightforward. That's simple because we start from smaller problem size. Then we use loop, right? For loop, while loop, we use some loop. So we can, iteratively move to problem size larger to the current problem size. Yeah. So that's the typical procedure. Yeah. All right. So here, starting with a solution smallest instance of the problem. Yeah. 0, 1, the base cases. Yeah. Then, using the iteration, so we increase the problem size gradually, incremental way, and finally, at the end, we solve the current problem size. So that's the way. All right. All right. So why sometimes, why not always? Yeah, because you said this way can save us a lot of memory space. Why we just do it all the time? Sometimes you cannot do it. Even if you want to do it, but you cannot. Too hard to do it. Yeah. Let's recall the Tower of Hanoi problem. Can you use the iterative way to do it? You cannot. Nobody can use the iterative way to do it. The only way you can do it in a neat way, the only nice way you can solve it, recursive way. Iteratively, probably someone works really hard, probably they can make it, yeah, but it will be very messy. Even if someone can make it, it would be extremely messy. Yeah, so you don't like to do in that way, although you can save some memory space. Yeah, but the reason many relatively difficult problems, you cannot use iterative way to solve. That happens a lot frequently. Yeah. All right, so let's move to next, insertion sort. Here I just do a simple introduction, and next we will solve in two videos. Next two videos I will solve. Here, the second half of this video, introduction. The problem still, problem 4. Old problem, sort an array. We revisit this problem. Yeah. This time we will take a different view. Yeah. We change our view so we can change the algorithm to solve it. All right, so this time we take this strategy. Start with simple case. With a simple case. We grow. Yeah. Iterative, right? Not recursive. Increase from smallest possible size, then grow the data size gradually. Okay? Yeah. Every time we just increase the problem size by 1, every time we add one more element, new element into the current array and get it sorted. Yeah. How to bridge the gap after you add a new element? How do you connect the previous solved problem and the current problem to be solved? How do you connect them? Bridging the gap. Yeah, so let's do that part. Yeah. So let us work on the problem size based on our intuition. Yeah, intuition. Yeah, very important here. When we start, we consider one element array. That's trivial. No comparison, nothing you need to do. It is sorted. Yeah. All right, next, add a new element, A1, into the current sorted array. So we can treat it as sorted array. No problem. Yeah. Now we add a new element into the current sorted array and get this new array sorted. That's easy, right? One comparison, you can do it. You only need to do one comparison. A0, A1, which one is larger, which one is smaller, then you can make your decision to get that two-element array sorted. All right, so now this two-element array is our already sorted array. So the next time we want to add a new element A2 into it and then get it sorted. How many comparisons do you need? For the worst case, not for the best case. Okay? For the worst case, how many more comparisons do you need? 2 more. Okay? 2 more. A2, A0. You may not get it sorted. A2, A1. Then you can get it sorted. The worst case. All right. All right. Yeah. But after it is sorted, A2 should be somewhere in the array, could be smaller than A0, could be between A0, A1, could be greater than A1. So there are 3 possibilities. All right. Then let's look at the general case. We add a new element to the currently sorted array, but for the general case. The general case, we have a k-element array. Okay? K-element array. But we need to add a new element into it, get it sorted by certain number of comparisons. So that's the problem description. Here we only describe what we are going to do to get the whole array sorted. Yeah. All right, the observation. Yeah. Our observation here, what we are doing, right now, basically just insert an element into a sorted array at the right position. We need to find its right position, then we insert at that right position. Here you can see we use this special word, term, insert. Yeah. So our next step, we need to study the insertion operation. Yeah. So